All right, in this video we're looking at measures of dispersion. And so the last one we talked about, the last lesson we talked about measures of central tendency. Now we're going to look at how we measure how spread out or dispersed data set is. So we're going to look at the range from raw data. It's called the standard deviation and the variance. We're also going to look at the empirical rule. And then although Chebyshev's inequality is outstanding, we actually won't be covering it in this lesson. So when we talk about this idea of dispersion, it's just the degree to which the data are spread out. And we have a couple ways of measuring that. The first is the range, and that'll be capital R. And the range is just the difference between the largest and the smallest. So you take the largest data value, subtract the smallest data, and that tells you your range of data. That's just one quick snapshot at how dispersed you are. Okay. But there are some little bit better concepts out there or ways to calculate dispersion, and one of those is the standard deviation. So again, all of these measurements are meant to describe, measurements of dispersion are meant to describe how spread out our data are. So in other words, how far on average each observation is from the typical data value. Okay, so standard deviation is based off of a deviation from the mean, or how far something is from the mean. For the population, the standard deviation about the mean for the ith, oops, I just highlighted the wrong one, but for the ith observation, so whether it's the 5th, the 7th, the 10th, whatever, is x minus mu. You just take that data value, subtract the mean, and that's the deviation about the mean. Then for a sample, you just take, that x by, whether it's the 7th, the 20th, the 30th, whatever the case may be, and subtract the sample mean. Okay, the further an observation is from the mean, the larger the absolute value of that deviation. Okay, and we say absolute value of the deviation because we could be below the mean or above the mean, but that absolute value will get larger. So when we look at all of the deviations, though, this is a nice little thing to note. When you take all of the deviations and you add them up, so when you take the sum of all the deviations, that will add up to 0, always, whether you are a sample or a population. So it's a really nice way to check yourself when you're trying to do and look at these deviations. And so you're going to take all those deviations, add them all up. They will be 0 as long as you've done it right. But, that just checks to let us know that we've calculated our deviations correctly. So now we talk about how we're going to find what's called that standard deviation. So we have the population standard deviation and then the sample standard deviation. So the population standard deviation is going to be the Greek letter sigma. It is the square root of the sum of the squares of the deviation of the population. So about the population mean divided by the number of population, or the number in the population. So that's a lot of English. But basically you take the deviation of the first, square it, the deviation of the second, square it, all the way up to the very last one, and square it, and then we divide by n, the population size. Okay, and this will give us the standard deviation. So here's kind of the short writing: the sum of the deviations squared divided by n, the population size. Okay, again, that's where x sub 1, x sub 2, x sub n, all of those are just observations from the entire population, though, and mu is our population mean. So if it's the population, you divide by n. The difference when you go into a sample standard deviation is we're going to divide by n minus 1. Okay, it's just a small adjustment, and we're not going to go into the reason behind that, but just know that the only difference there is you're going to divide by n minus 1, and the sample standard deviation is s. So if we are comparing two populations, The larger the standard deviation, the more dispersion the distribution has, provided that the variable of interest from the two populations has that same unit of measure. If one is in meters and the other's in inches, okay, we're not comparing the same units of measure, so they've got to be the same units of measure. Now we look at this term called the variance. The variance of a variable is the square of the standard deviation. So the population variance is sigma squared, and the sample variance is s squared. And they're simply found by just taking those standard deviations and squaring them. But the units of measure in variance are squared values. So like it would be dollars squared, yards squared, seconds squared, or something like that. So as you can see there, it makes it interesting to interpret the variance when we have squared units. But it is important for calculating or conducting certain types of statistical inference that we will discuss much later on in this class. But just know the relationship between the standard deviation and the variance is the standard deviation squared, or the standard deviation times itself. Okay, so we're going to look at, we will do a couple of these by hand, and you'll see that they're quite tedious, and then we will use StatCrunch to help find the rest. But so we've got a sample population. Here are all of our data points. We've got 5 of them. So first what we need to do is we need to find x bar, which would be 20 plus 13 plus 4 plus 8 plus 10. All of that divided by the quantity of 5, which gives us a standard deviation, a mean of 11. Okay, now the fun part, finding the standard deviation. So first we have to find the value, which in terms up above are the x sub I term. So we're going to have our values. Get my table set up here. So our values are 20, 13, 4, 8, and 10. Then the next thing we're going to do is we're going to calculate those deviations. So it'll be x minus x bar. So the deviation for the first one will be 20 minus 11, which is 9. And then the next one will be 20 minus 13, which is 7. And then, oh, why did I do 20 minus 13? What am I doing? Okay, and then you do 13 minus 11, which is 2. 4 minus 11, which is negative 7. 8 minus 11, which is negative 3. 10 minus 11, which is negative 1. So there are our deviations. Okay, so now we've got all of our deviations, and notice if you were to add them all up, okay, the sum of those deviations, so the sum of x bar, of x sub I minus x bar is equal to 0. Okay, then we're going to look at the deviations squared. So you'll have 9 squared, which is 81, 2 squared, which is 4, negative 7 squared, which is 49. Sorry, I know handwriting's bad, but this just becomes tedious. Negative 3 squared, which is 9, negative 1 squared, which is 1. So when I add up the sum of the deviations squared, that is equal to 144. So to find our standard deviation S, we take the square root of the sum of the deviations squared, which is 144, and we divide it by the sample size minus 1. So 5 minus 1 is just 4. So this becomes 12 over 2, or 6. So that's how we'd find the sample standard deviation. The variance would just, you'd take the 6 and you would square that value. Or, whoops, sorry, I had a little glitch there. All right, there it comes. All right, now we have the population, so we want to find the population standard deviation. So the same thing, we're going to find the mean, which is 3 plus 6 plus 10 plus 12 plus 4, divided by our 5 terms. Okay, and that is 9. So then we're going to look at, or have each value, and again this was like the x sub I. Okay, so they were 3, 6, 10, 12, and 4. And then we're going to look at those deviations. So you'd have 3 minus 9, which is negative 6. And then you have 6 minus 9, which is negative 3. 10 minus 9, which is 1. 12 minus 9, which is 3. And 4 minus 9, which is negative 5. Oh, this is 14. So 14 minus 9 is a positive 5. So yeah, that should be a 14 right there. Okay. Now we're going to take those deviations and square them. So you'd have negative 6 squared. And whenever you square a negative, it's always did that wrong. It's always positive. So negative 3 squared is 9. 1 squared is 1. 3 squared is 9. And then we get 25. So the sum of the deviations squared here is 80 when I add all those up. So then this population standard deviation is the square root of 80 over 5. And 80 divided by 5 is 16, so it'll be square root of 16, or 4. So sigma, the standard deviation, is 4. The variance, just again as a note, would be 4 squared, which is 16. Okay, so that's a look at how we would determine these by hand. Hopefully you can see that this is a pretty tedious process, and so we're going to yield to StatCrunch to help us out in finding some of these more difficult standard deviations. Okay, so this next one we have the acidity or alkalinity of a solution is measured in pH. pH at less than 7 is acidic, while greater than 7 is an alkaline. So we've got tap water versus bottled water. Okay, which type of water has more dispersion in pH using the range as a measure? So to use the range, I've got this pulled up right here. Okay, so I got all my data in. I'm going to go to Stat, and I'm going to go to Summary Stat by column. I'm going to highlight both of these, and then so you can see here highlighted is the range. So I'm going to hit Compute, and the range of the tap water is 0.59, whereas the range of the bottled water is 0.26. So when we look at the range here was equal to 0.59, whereas the range for the bottled water was equal to 0.26. So there's much more dispersion in the range of the tap compared to the range of the bottle water. So that the range is very simply calculated. Again, it's just the biggest value, subtract the lowest. So for this first one, that would be 7.69 minus 7.1, which is equal to the 0.59. And for the bottled water, it would be, the biggest I see there is 5.28 minus 5.02, which is the 0.26. Okay, so that's a look at the range. So I'm up against the clock, and we'll continue this problem in a part 2.